All right, welcome back to another exciting data analysis lecture. Um, let's go ahead and get started. So in this lecture, we are going to talk about some miscellaneous facts. And though they are not maybe directly related to the flow that we've gotten started in, as far as talking about what is an optimal estimator, we talked about some inter-statistical modeling, some of these big ideas about what does it mean to do prediction well, and how can we quantify a model's generalizability so that it's flexible but not too flexible. We've talked about all these ideas. This is sort of a little aside where I want to make sure that we're all on the same page about some prerequisites. I expect you've heard of all these before, but I just want to state them in this course in a concise way where you have a bunch of slides that you can reference to say, oh yeah, we talked about that. So let's go ahead and get started. So just some basic probability notation and definitions. So if x is a continuous random variable, okay, with some density p of x, its expectation of x is defined as follows. So you take the integral x, multiply with times the density, you take this integral, okay? So you integrate x against the density, and if x is discrete, then you have a mass function, a probability mass function instead of a probability density function, and then the expectation is we replace the integral with a sum, right? So this is pretty standard. And the variance of x is defined as expectation of x minus expectation of squared x. I mentioned this, so this is the expectation of the square x minus its own expectation. So this is the sort of average squared distance between x and its expectation. This is the definition of variance, where how you actually evaluate this depends on if x is discrete or continuous, whether you use an integral or a summand. I'll mention here, this is just a small aside, but what do I mean by all x here? I mean all x in the support of the random variable, that is all possible x's. So this is a variance. The covariance of x and y is the following. So you take the expectation, but instead of having a squared here, the covariance is you multiply x minus its expectation times y minus its expectation. Okay. And the idea here is, you hope you have heard this before, but covariance captures how much x and y trend together, right? So let's say that x tends to be above its mean when y tends to be above its mean, right? Then this will be positive when this is positive, and this will be negative when this is negative, and the covariance will end up an expected value of a bunch of positive terms. Whereas on the other hand, if they trend in a negative direction, x is below its mean when y is above its mean, or vice versa, then this quantity is negative, and you're taking the expectation of a negative quantity, and covariance ends up being negative. So just some basic definitions there. Some facts about expectations, variances, and covariances that we're going to use frequently in this course. We've already used some of them. Expectation is linear, so you can distribute it across sums, and you can pull out constants. Okay, so that's what I've done here. Distribute across the sum and pulled out constants. We have a variance shortcut. I also mentioned this in a previous lecture. Variance can be written as expectation of squared minus square root of expectation. If you have not seen that, you can just sort of write out this. You can square this. You can expand this square, distribute the expectation, and get it. There is a similar covariance shortcut to a variance shortcut where you take the covariance of x and y. It's the expectation of x times y minus expectation of x expectation of y. Again, it follows from the same reason that you can distribute. You can sort of expand this multiplication and distribute the expectation by linearity across each of the terms. So these are the shortcuts. Covariance is symmetric. The covariance of x and y is the covariance of y and x. Well, why is that? We can just look back on this, right? If you change the role of x and y, you just change the role of this multiplication, which obviously you can multiply in any order you want. So covariance is symmetric. The other thing is that the covariance of a random variable with itself is that random variable's variance. So the covariance of x with itself is equal to its variance. Okay, why is that? Well, again, if we look here, covariance x and y, right? What if we plugged in x for the second y argument? We would get expectation of x. This would be x minus expectation of x. This would be x minus expectation of x. And we would get a square x minus expectation of x, which is just the definition of the variance, right? So, yes. All right. More quick rules coming at you. The variance rule for linear transformation. So this one, I think, is the one students have most trouble with in this course, is sort of remembering the fact. Once you get it, it will be fine, but it takes some time to get it in there. So the variance of a linear transformation of x. So you're taking the variance of ax plus b, where a and b are constants. Well, the b doesn't affect anything. This is just a constant. And the a can actually come out, and when it comes out, it is squared. So the variance of a times x is, or the variance of a times x plus b is a squared times the variance of x. Okay? And you can actually see that. I don't want to be too detailed in terms of justification, but if you added a b to the x, if you multiplied by a and added b to all these terms, the b's would just cancel straight up in the subtraction, and the a's could get pulled out of the square, and then because they'd be a squared and can again come out of the expectation. You'll use these really regularly in this class, so it's better to just commit them to memory, but you can just go back to the definitions and justify them there. The covariance rule for linear transformations is very similar. If you have ax plus b only in one argument, right, what happens is instead of pulling out and squaring, you pull out just the a, right? So the b again is negligible, and you can pull out the a covariance of x and y. And this one I'm not going to. You can look at the definition; it follows very easily. The variance of a sum, variance of x plus y, can be expanded as follows. So the variance of x plus y is the variance of x plus twice the covariance of x and y plus the variance of y. Okay. Now, this is important. This is important as a theme, so I'll just mention it. Variance behaves just like square, right? So if variance behaves just like a square, so what does this mean? What do I mean by that? I mean that this looks like you squared x plus y. You got x squared plus y squared plus twice x times y. Right? This looks just like you expanded a quadratic. And that's exactly what happens for variance. And it's sort of unsurprising that it looks like a square, given that its definition is this square, right? So if you added x plus y here and you just expanded this, you would see exactly what I've just described, that you get this expansion. So variance of a sum, you can't just do the variance of x plus y is variance of x plus variance of y unless their covariance is 0. Okay, so that happens in particular when random variables are independent. They're uncorrelated, meaning their covariance is 0. But in general, you can't assume that. With this theme that the variance performs like a quadratic, you can actually perform the variance on a big sum by basically exactly the same thing. You can sort of do this sort of square expansion just like you would if you were working with square instead of a variance. You take the pairwise covariances between all the random variables. The covariance of a variable with itself is its variance, as we described. So you can sort of, and also this thing is symmetric. So you can expand this variance into a bunch of covariances, and then collect their sort of, when I equals j, this is a variance. And then there's these ones where I does not equal j. But every time that I does not equal j, there's a time when you have I, j, and there's a time when you have ji. So you can combine them and just double them. So this is the variance of a big sum, can be written as the sum of this covariances, which is the sum of, which can be again written as the sum of variances plus, and then you have this covariance term here. And notice I've written this second index as j greater than I, And when I do that, I make sure that I don't double count. I'm only counting an ij pair once. All right. So we talked about this before. This is the law of iterated expectation. We referred to it in the previous lecture. So it's the fact that you can apply this iterated expectation, an outer expectation, an inner expectation, where your inner expectation conditions on another random variable. Because this thing is constant on that when y is some value, you can think about this outer expectation as taken with respect to that conditioning variable. Okay. The law of iterated expectation has an analogous sort of law for variance, where you can do this conditioning on y to get an expression for variance, where you can write variance of x is the variance of the conditional expectation plus the expectation of the conditional variance. Okay, this is called the law of total variance. And then lastly, on this slide, I will say that as I mentioned before, independence of x and y gives that the covariance is 0, but the reverse is not true. Okay, so if x and y are independent, they're uncorrelated, their covariance is 0. But in general, covariance being 0 does not mean that the random variables are independent. There are some special cases. The special case in which this goes backwards, covariance being 0 implies independence, is the Gaussian or the normal case, where x and y are normal. All right. So some important theorems, not just some important definitions and facts. Important theorems. The first one is the law of large numbers. So the law of large numbers says that if x1 through xn have 0 covariance with each other and the same expected value, okay, then the sample mean converges as n goes to infinity to the expectation of x. Okay, so what that means is sample mean converges to the true expectation. This is sort of as you would expect, right? As you take a large number of samples, the sample mean collapses onto the true mean. Okay, so the law of large numbers has sort of a funny name, but it just formalizes that. Says that if x1 through xn have 0 covariance and the same expected value, then you get this convergence. Okay, so the sample mean converges to the population mean as the number of samples gets large. Another important theorem, which you've seen in your statistics class, is the central limit theorem. One statement is as follows. So if x1 through xn are IID, that is, they are independent and identically distributed, so they all have the same distribution and they are independent of each other, then as n goes to infinity, okay, so as the number of samples goes large, the sample mean, which I've just written out here, has a distribution which is normal, mean expectation of x, variance of x over n. Okay, so the variance is divided by n, the mean is expectation of x. Okay. And notice this does not depend, this is sort of the magic of the central limit theorem, this does not depend on the distribution of x. It can be whatever distribution that there is. Right? So, but yeah, so another way to write this, if you write this as a standard normal random variable, so you can take the sample mean, subtract off its mean, divide by its standard deviation. Since its variance is variance of x over n, its standard deviation is square root of variance of x over square root of n. You get that this property, or this expression on the left-hand side, this is a standardized version, converges to the standard normal distribution. More miscellaneous facts, as is the title of the lecture. So those are important theorems. Some vocabulary. So if we have a sample, so we have n samples from some distribution, a statistic is a function of this sample. So a function of a sample is a statistic. That's where the name statistics come from. And an estimator is a statistic, so as a function of the data, which tries to estimate some population parameter. Okay. So an estimator, in general, an estimator is random. It depends on the sampling distribution. It depends on the sample, right? So an estimator statistic, because it depends on the data, it's random, okay? The distribution of an estimator is called its sampling distribution, right? Again, I hope you've heard these in your stats class, but if not, this is just a quick review. And so how can we describe properties of an estimator? So an estimator is called consistent. Okay, so this is an estimator that is, it's built on n data points. It's an estimator of theta. So it's an estimator is consistent for some parameter theta if the estimator converges to the truth as n goes to infinity. Okay. An estimate, the bias of an estimator is the expected value of the estimate minus the truth. Okay. So these are sort of complementary in the sense that an estimator being consistent means that as I get more and more data, I get closer and closer to being right. That's sort of an intuitive property for an estimator to have. Okay, and a bias, the bias of an estimator. So if an estimator is unbiased, it means that its bias is 0. An unbiased estimator says that I am equal to the truth on average, right? So these are different because you can imagine if my estimator is just if my parameter is some point, let's say it's at 0, and then my sampling estimator stays like this. So this is for all n. The sampling distribution of my estimator looks like this. So this is the distribution of my estimator. Well, on average, I'm equal to the truth, right? So the expectation of this distribution puts me right at the truth. But I'm not consistent unless this distribution sort of collapses onto this point, right? So the bias is capturing something different than consistency. Consistency is a limiting behavior that we collapse to the truth. Bias is saying on average I'm good, right? We can have an estimator which is biased, but collapses to the truth. If you can imagine, like this is slightly off to the left, but as n gets large, it sort of becomes a spike, and the distribution collapses onto the point, right? So these are different notions. So we have bias, which is an expectation. The standard error of an estimator is its standard deviation. Okay, so in general, low bias, low standard error are good because they're saying on average we are close to the truth, and then the standard error being small says that this distribution is not too fat, right? Even if we're good on average, even if we have fat tails where sort of we can be far away from the truth, that's bad, right? So we want the standard error to collapse to 0. This says that in combination with being unbiased, this says that the center of the distribution is at the truth, and then the distribution is not too spread out around the truth. All right, so here's an exercise. So here's a problem just to help you parse all these definitions. So if x1 through xn is IID, again, that means independently, identically distributed, is the sample mean consistent for the true mean? Okay, so is the sample mean consistent for the true mean? So we have an IID sample. These are all independent, identically distributed. Is the sample mean consistent for the true mean? I've written x1 here. I can write x1 because all these x's have the same expectation because they're identically distributed. It's all the same. Okay, so I'll pause, you can flip through the slides, see if you can answer that question. Okay, so I'm gonna go ahead and answer, so pause if you need to, but the answer is yes, it is consistent. Why does the sample mean converge to the true mean? Well, we've seen that before by the law of large numbers, right? So let's jump back to the law of large numbers. The law of large numbers says that if x1 through xn have 0 covariance with each other and the same expected value, then the sample mean converges to the true mean. Okay, well, I have that the x1 through xn are independent, right? If they're independent, we've talked about independence means that their covariance is 0. So they have 0 covariance with each other, okay? And then we have a sample mean, which then converges to the true mean. So it follows from the law of large numbers and the fact that independent random variables have covariance to them. Okay. All right, so that's all I have for miscellaneous facts. I look forward to seeing everybody at the next lecture.